So let's start the class. So yeah, I realized so I was sort of behind my schedule this week. So or this past week, I suppose. So I have several project emails, project proposals by some of you that I'm yet to respond to. So I'm sorry about that, and I'll try to get to them today or tomorrow at the latest. Yeah, and for this coming week, we will cover the um, the gamma 2 norm in communication complexity. If anybody already knows they would like to volunteer to present, maybe we can have people sign up now. So I should mention that after this class, everyone will have presented at least once, and I think 3 people would have presented twice. So if you presented twice, you're not going to present again until the final project presentations in the last week. But there should be 9 people who only presented once. So any of those 9 could volunteer. If not, that's okay. I can send emails out for a randomly selected group of people. Okay, fair enough. So another kind of logistical note is that one of the people presenting today, Olivier, just emailed me half an hour ago to say that he had some last minute issue and can't make it to the class. So I guess he's going to send me the slides, but he won't be able to be here to present today. So we'll see whether we can fit him in next week and do kind of 4 next week, or whether we'll just have to post his slides and skip the presentation altogether. So that will be an issue to figure out for next week's schedule. So we will have 2 presentations today. So maybe we'll actually finish by 5:30 for once. Well, we can start with the presentations, but right, I guess, yeah. So I was gonna ask if anybody had kind of comments on the reading assignments on the papers, but maybe it makes sense to first see the presentations on them and then take up comments on them. Okay, so the 2 people who are here and will present are Danny and Tony, I guess, if I recall correctly. I can check my spreadsheet, but do either of you have a preference for who wants to go first?
I don't particularly care.
Okay. Well, which paper were you presenting again? Sorry.
So I'm presenting the oracle separation between BQP and the polynomial hierarchy.
Okay. And
I was presenting separations and query complexity using cheat sheets.
I see. Okay, so yeah, those are sort of independent of each other. They don't use each other's. So there's no particular natural order. I don't know if either of you have a preference for who goes first.
Well, I can go ahead then.
Okay. Yeah, go ahead.
Okay, let me set this up here. Screen number 2. Okay. So the paper I'm presenting is about the oracle separation between BQP and pH. And so just kind of jumping right in, the main result here is that Raz and Tal explicitly give this distribution D over plus or minus 1 to the 2n such that there's a quantum algorithm that can distinguish between D and a uniform distribution with some advantage. And whereas this AC0, which I'll define in a moment, family of Boolean circuits, cannot distinguish between D and the uniform distribution with advantage better than this polylog n over square root n. And so it turns out that asymptotically, this is indeed better than the classical version. And then so they use some kind of standard reduction techniques, and then they show that this promise BQP class is not inside this AC0. And so it shows that also this promise BQP is not in promise polynomial hierarchy. And then there's a result from Aronson that shows that if this is the case, then there exists some oracle that BQP to this oracle is not in the polynomial hierarchy to this oracle. And so the relevance of this is that this gives us a little bit of hope that maybe BQP is really not in polynomial hierarchy, because it could be that this oracle is the null oracle that does nothing. But then again, it's not a definite thing either, because like for instance, we know that IP equals P space, but there are a lot of oracles where IP is not the same as P space. So some definitions here. So we define that an algorithm A distinguishes between these two distributions, D and D prime, with some advantage epsilon if the probability that A accepts something from the distribution 1 minus the probability that they accept from distribution 2 is this difference is epsilon. So basically, this just means that there needs to be you want to have your algorithm accept more for one distribution and reject more for the other distribution. And then so this AC to the K class is this class of languages that's computable by families of Boolean circuits. And it's different than P over poly in that these Boolean circuits allow for unlimited fan-in and they have a bounded depth. In this case, order log k or log to the k of n. So in this specific case, AC to 0 requires some constant depth. And so I'm also going to assume you guys have some familiarity with the polynomial hierarchy, BQP and promise problems, but if not, let me know now. Is there anyone? No questions? Okay. So getting to the main meat of the paper. So the big thing is that they're trying to distinguish D from the uniform distribution. And unfortunately, it's a pretty technical result. And the main basis of their result comes from this correlation problem, which is described by Aronson and Binus. And in there, they show that there's like a separation between the relational versions of BQP and polynomial hierarchy. And their problem has to do with whether a function is correlated with the Fourier transform of another function. And so specifically, this distribution D, the way you get it is first by getting this distribution G prime, which is a slight modification of the correlation distribution. And the idea is you first sample these x1 through xn from real numbers according to a normal distribution with variance epsilon. And epsilon in this case is just some constants. I think it's like 1 over 24 log n, something like that. And the idea is that they just want to have this be relatively small. And they have this second vector, which applies the Hadamard transform onto this x that was generated. And then the overall output is this z, which is a vector that's the concatenation of x and y. And then from this z, you get the distribution d over because so G prime is over real numbers, a vector of real numbers. But now you want to get specifically these strings of plus or minus 1 to the 2n by you first sample Z, and you end up truncating each vector element of Z to the interval -1 to 1. And then you actually draw Zi prime, which is going to be plus or minus 1, with this probability based on the truncation of Z. And then you output the Z prime as this new vector of plus or minus 1. And so the reason that they bring up this, well, so one of the main points in the paper is that this distribution D acts very similarly to G prime under some multilinear map. And they use this kind of multilinear map more in the showing a classical lower bound, but that part is, again, very, very technical. But so for the quantum side of things.
Oh, sorry, quick question.
Yeah.
Why do they choose to do 2n length plus or minus 1 strings instead of 2n length binary strings?
I'm not quite sure. I think it has to do, again, with the way that these distributions are used in the kind of classical lower bound. But the idea for the quantum case is that these that this xy ends up being a belonging to a linear subspace, actually, of this R at the end, since this Hadamard transformation is a linear map on X. And then so basically they want to accept something with that's kind of closer to this linear subspace rather than just a uniformly distributed string.
Yeah, so just in terms of the plus minus ones, so of course it doesn't actually make any difference because these are just alphabet symbols, but it often it simplifies the notation to denote things with plus or minus ones depending on what you're doing. So in this case, they are sampling normal distributions and truncating them and whatever, or so when you do things like that, then it's more natural and makes the notation easier to have the mean of these distributions be 0, of a normal distribution to have the mean be 0. And that way you have equal probability on plus 1 and minus 1. So that's kind of a more natural thing to do than to try to have a distribution on 0 and 1. So given the way they're setting up their analysis, the plus minus 1 notation is just more convenient.
Okay, cool. Thanks, both of you.
Okay. Let's see. So, right. So again, the classical lower bound is pretty complicated. They use some. There was a result that Tall had before about some tail bounds on Fourier coefficients, and then a lot of some other recent work, but it's kind of complicated. And then so after they get this result, and then they show this kind of separation between how well the quantum circuit can distinguish versus this AC0 Boolean circuit, they do some reductions. And so what they first do is they use some amplification techniques so that they find a new distribution D and U based on D in the uniform distribution to widen the advantage gap. And using that, they show specifically that BQP is, or promise BQP is not in promise AC to the 0. And based on this, they form a relationship between promise BQP and promise polynomial hierarchy, because polynomial hierarchy is related to AC0, and the way that this can be shown is that in the polynomial hierarchy, the way you can express every problem is with this kind of use of these quantifiers, where if you can have a string of exists for all, etc. And if you're allowed to have these Boolean circuits with unbounded fan-in, you can convert these existential quantifiers into ORs and universal quantifiers into ANDs. And by doing that, you can actually create a circuit that evaluates things in the polynomial hierarchy. And then so based on that, they show that this result here, where promised BQP is not within promised polynomial hierarchy. And then, as I mentioned before, there's a result by Aronson, which shows that once you have this difference in promise classes, they can construct explicitly an oracle from the distributions to show that in this oracle there's BQP is not the same as polynomial hierarchy. And yeah, that was the result of that paper. Any other questions? If not, then I will stop sharing here.
All right. So thanks, Tony. So yeah, I'll say a few words about this paper as well. So yeah. So I mean, I guess right. Maybe the main or kind of the main thing you're understandably skipping over is why a connection between kind of separating quantum query complexity from AC0 has something to do with separating BQP and pH, and that's fine. You as you said the previous paper of Aronson, but roughly so roughly speaking, separations exponential separations in query complexity for partial functions are going to give oracle separations in sort of the Turing machine model, and that's just true for most pairs of complexity classes. And the intuition. So very roughly, if you have a query complexity separation, then you know there is some function that, say, one model of computation, maybe quantum computation, can solve, and classical computation cannot. And we can think of this function, the input to the function, we can think of the input x as basically being a black box that you make queries to. So, if these black boxes existed out there in the real world, then quantum computing will be more powerful than classical, provably, and in fact more powerful than even these other classical models, such as polynomial hierarchy in this case. So now this is sort of trying to say that if certain types of black boxes could be found in the wild, then we could prove quantum computation gives an exponential speedup. Now, an oracle separation is a statement that's kind of similar to that. If you think about it, it tells you, it says, okay, so if there existed an oracle, like if a Turing machine had access to an oracle where you ask it a question and it gives you back an answer on a special tape of the Turing machine or something like that. So then what can you solve? And when we want an oracle separation and we want some kind of oracle such that kind of a quantum polynomial time Turing machine or whatever with access to this oracle can solve some task that a classical one cannot. And if you think about it, the way we phrase these two settings is very similar. In one setting, we have these black boxes living in the wild. In the other setting, we have this oracle living in the wild. And the main kind of difference is that in the one case, we have the oracle that takes in inputs of arbitrary length, of any length, and returns answers. But we only have one oracle. And in the other case, we have these black boxes take input of fixed length. That they just act, they're fixed black boxes that just have input wires. and they take in like inputs of length, some n, but there's many black boxes. Even for a single n, there's going to be many possible inputs x to the function. So that's many possible black boxes. So there's going to be many black boxes living out there in the wild on which you want to solve a certain task. And so converting between one of these settings to the other is not completely obvious, but there is a way. There's like a thing called it's often called slow diagonalization, where you try to eliminate the classical Turing machines by correctly, like your oracle will choose which black box to return answers from. You construct an oracle that kind of returns answers from a certain black box in a way to kind of make each classical Turing machine fail. It kind of diagonalize across the Turing machines. Via a technique called slow diagonalization. So that's a little technical. And people usually skip over that part to just say, yeah, standard techniques. Therefore, a query complexity separation implies an oracle separation. But that's what's going on behind the scenes. It's this conversion between these kind of black boxes that are basically the query model to an oracle, which it almost sounds similar, but when you formalize it, you realize it's not actually the same, and converting between them is actually pretty tricky. But it's a standard tricky thing. Like it's been done many times since like the 80s and 90s. People keep doing it for different classes of models, and it's kind of considered standard right now. So that's sort of what's going on there. Then there's the question of why is AC0 the same model as polynomial hierarchy? So kind of for the quantum models, you even give them the same name. You called both of them BQP, I guess. But you can ask, why is the polynomial time quantum computing for Turing machines, why is that the same as quantum query complexity? So and then it turns out that for the in this conversion, when we want to convert an oracle separation to a query problem, to reduce it to just a query separation, then polynomial time quantum computation in the Turing machine model becomes quantum query complexity with polylog many queries. Like you want the number of queries to be at most polylog n, where n is the input size. So it turns out that's the right way to convert polynomial time quantum computation to query model. So the polynomial time part became polylog number of queries. So kind of the input size became, in a sense, log n instead of n. That's sort of how many wires there were to the black box, where the black box has n possible inputs it can take in, but to specify one input, you only need log n wires of bits that tell you which index you're querying. So so basically there's been a change in what we call the input size. Before we called it n, but n was actually the maximum number of queries. But now we want to call the input size log n. And so polynomial time will sort of be polylog n queries. So that's what happens for how you convert the quantum model in Turing machine world to a quantum model in query complexity. You just say, okay, instead of polynomial time, we call it polylog queries. And what happens classically is kind of what you're getting at the end there. So polynomial hierarchy, I don't know how many people even know this model. Depends on kind of whether you've been exposed to it in some complexity class. But it's a model that kind of generalizes NP. It's kind of much larger or much stronger than NP, and it's kind of saying, what if you had the ability to ask for, like you had the magical ability to press a button and solve NP complete problems, and and then you can ask, okay, so which problems can you solve if you had such a magic button? And there may be problems that you still can't solve even with this button, but you kind of can verify a proof that the answer is no. So or you can verify a solution using this magic button, even though you cannot solve. So it's kind of relative to this magical button. There's a new definition of P and NP, basically, where like now you can solve NP problems for free, but there's kind of new meta NP problems that you can verify the solution to, but cannot solve even with this magic button now. but you can only verify the solution using the button. Anyway, so you can define, and then so you can imagine a button that solves these problems too. And you get a hierarchy of different levels of NP. Basically, this is called the polynomial hierarchy. So PH, the class called polynomial hierarchy, allows you to use any button for any fixed number k of levels of nested NP problems, basically. So it's kind of a tricky thing to even define, but the way it's usually defined has a bunch of alternating quantifiers. Like it has a instead of just there exists a witness such that some polynomial verification accepts, then this polynomial hierarchy is defined using quantifiers, and the problem has to look like there exists a witness such that for all counter witnesses there exists a secondary witness such that for all secondary counter witnesses there exists a third witness such that some computation accepts. So when you have these nested alternating quantifiers and you have a constant number of them, a number that does not depend on the input size, then you get a problem in polynomial hierarchy. And that turns out to be a characterization of the class. And so it turns out that when you try to scale everything down, when you try to kind of, so in query complexity, you kind of, well, you turn n into log n and you try to make everything in terms of queries or whatever. Then these for all n exists quantifiers basically become and or gates. It kind of makes sense that if you're trying to say all witnesses do something or all counter witnesses do something or something, then you're putting an and if you're trying to say there exists a witness such as something accepts, you're basically doing an or over the witnesses. So you get these nested and or gates of kind of polynomial width, like they can be pretty wide, but constant depth. And so you're basically getting a circuit class where you take the original bits of the input of the input x, you kind of feed the bits of the inputs into these and or gates that have kind of large fan-in, but only constant depth. And then and then you try to compute the function using this model, and that model is called AC0. It's kind of a weakish circuit class in that it's weak because you have very little depth. You have constant depth only. So anyway, so this is how you get AC0, and we know how to prove lower bounds against AC0, like it's but only in some circumstances. So it's generally, it's considered possible to prove that various functions are not in AC0. For example, we can show that the parity function cannot be computed using such a circuit. You need more depth than that. So you can't compute parity using like a constant depth circuit of and OR gates. But although we're kind of pretty good at proving AC0 lower bounds, it turned out that specifically constructing a problem where quantum query complexity is polylog n, is small, but there is no AC0 circuit lower bound, was a very challenging task that was open for many years. So this paper basically finally proved it using a variant of this forwardation problem, I guess. Okay, any more questions about this paper? All right. Well, let's go to the other paper and see if we want to discuss both of them later.
Okay.
Do you want to do the second?
Yeah, let me share my screen. Okay. I'm gonna just present on the paper called Separations in Query Complexity Using Cheat Sheets. So I'll start by just a little motivation. Basically, like the idea is we want to always be trying to look for like the best case separations between like classical, randomized, and quantum query complexities of total functions. So this is a paper that is basically working towards that. So for a long time, there was we knew about Grover's algorithm, which produces a quadratic speedup between classical and quantum, and it was like a pretty widely held belief that this was kind of as good as we can get for these types of functions. And then pretty recently, it was shown that you actually can get better than quadratic speedups when you're comparing between the zero error randomized complexity and the quantum complexity, which is allowed some bounded error. And then, so we're kind of interested in the case where like both randomized complexity and quantum complexity are allowed some small bounded error, because there might also be a gap between like the zero error complexity, randomized complexity and the actual randomized complexity. So we're kind of comparing two like things here. There's some prior work on this. So the NAND tree problem shows that there's like about a 1.3 like power, like the exponent is 1.32 between the deterministic and the random randomized complexity, even when there's zero error. The OR function is an example of a total Boolean function that has a quadratic separation between quantum and classical, randomized or otherwise. And then this recent work was one that showed that there was actually up to a fourth power speedup between quantum and deterministic classical query complexity. And there's like a cubic speedup between the randomized and quantum complexity in the zero error case. So the work that I'm presenting today kind of fits in somewhere around here. So we're looking at the bounded error randomized case compared to the quantum case. And we're trying to get a better than quadratic speedup. So that's kind of the setting. So this paper introduces the technique of cheat sheets. Essentially, the idea is we're going to take a function, and maybe this function is not going to be a total function, but we're going to transform it into a better version so that we can kind of like do a better analysis and get a better speed up. So an example of a problem that we can choose is the correlation problem. And this problem is pretty nice. It has a square root in speed up. The classical complexity is square root in, or the randomized complexity, and the quantum complexity is O1. So the idea is we're going to take this problem, we'll call it G. The G function is the correlation problem, and H is the and/or function, which is a total function. And then we're going to compose this function in this way on n cubed qubits. And then, so although f is still partial, we can kind of hide some information for the quantum algorithm to use that the randomized algorithm can't really access quickly. So we're gonna kind of like give like a cheat sheet and kind of help the quantum algorithm without helping the randomized algorithm. So one way that we can give information to the quantum algorithm is by the value of querying like f on a particular input. So the idea is we can store a very large array, and in this array we can hide some cheat sheets at certain addresses. And then so a particular cell of the array might have contain some certificates that we can use. And the idea is, so let's say we have an array of size n to the 10, which is a very, very large array. We can use 10 log n queries to encode a particular position by making our quantum algorithm query those positions in, I guess, like n log n time, and then use the information at that position of the array to aid our quantum algorithm. So an example of some information that we can encode here is we can have a certificate to prove that this input is actually in our domain because f is still a partial function, and so on. And this is basically the general idea behind the main technique of the paper. And then using this technique, they prove some results which can be summarized into 4 theorems. So theorem 1 basically states that they give an example of a function where the speedup over the randomized algorithm in the bounded area case for both is power 2.5, so it's better than quadratic. And there exists a total function where the query complexity is 4th order power, like there's a 4th order power gap to the approximate degree. So the approximate degree is something that we would normally use in the polynomial method to give a lower bound of the complexity. And this actually shows that might not always be good because there's a like 4th order gap to this lower bound. There also exists a total function which has some complexity that is quadratic in the certificate complexity, that's at least quadratic. And there's a total function which has query complexity that is quadratic in the exact degree. And then there's also some reproduction of other work within like the cheat sheets framework. So using the cheat sheets framework, there is some reproduction of other work that is done in other methods. So that's basically an overview of the paper. Are there any questions? It was kind of short.
Okay. Yeah. Thanks, Danny. Yeah. I mean, if nobody has questions, I'll say a few things. I guess as usual. So, right. So, part of the sort of the main thing this paper is doing is it can convert partial functions into total functions while maintaining this cheat sheet framework converts partial function into total functions while maintaining a little bit of the original separation. So, I mean, of course, we know, if you remember from like the first week, that for total functions, there's a polynomial relationship between different query models like the randomized and quantum query complexities and deterministic as well. So all of these types of algorithms in query complexity are polynomially related to each other. And that's for total functions. For partial functions, it's usually pretty easy to find separations. And we had, for example, Shor's algorithm that gave an exponential separation between quantum and randomized query complexity. But there's a few other examples. And there's also exponential separations between randomized and deterministic query complexity for partial functions. So we know that we're not going to successfully turn a partial function into a total function while maintaining the separation, right? So that's not going to be possible because in partial function setting, we have exponential separation. In total function settings, we know that's not possible. So instead, what this paper is doing is well, it converts partial functions into total functions anyway, and retains a little bit of the separation that was there earlier. So it in particular, so it takes a separation, a partial function separation that gives you that has randomized query complexity root n and quantum query complexity 1. So a kind of O1 versus root n separation for partial functions between randomized and classical. So it takes that and converts it into a total function where there's a power 2.5 separation between quantum and classical query complexity. So basically, if you just did Grover search, you would get a quadratic separation, and so this procedure uses Grover search. It uses this quadratic speedup that we already know how to get from quantum computing, combines it with this exponential separation for partial functions, and gets a slightly better than Grover speedup separation for total functions. So and you can do that with any partial function, and you would get some separation for total functions that that depends on how big your partial function separation was. And the paper that Olivier was going to present today, so that he might present next week instead, because he wasn't able to make it. So that the last paper for today was going to be about how to get a larger separation for partial functions, and n versus log n separation for partial functions between randomized and quantum query complexities. So once you get an n versus log n separation, then applying this cheat sheet framework immediately gives you a cubic separation for total functions. Okay, so kind of the maximally large separation for partial functions converts into a cubic separation for total functions. Now, actually, the upper bound we have is power 4, so we know that the relationship between randomized and quantum query complexity is at most power 4. And now, because of this combination of cheat sheets with this largest possible partial function separation, we know that the largest separation between randomized and quantum for total functions is at least 3. So we know this gap, the maximum gap between randomized and quantum query complexity for total functions is between 3 and 4, but it's open what it is. Okay, so but the 3, the way to get the 3 is to use this cheat sheet framework that converts a partial function into total functions, combined with the largest possible partial function separation, and then the number you end up getting is 3. Yeah.
I kind of have a question. So maybe this, I didn't really kind of talk about this, but because I didn't totally understand it, but I felt like it was important. So I guess on this slide, we chose a particular, or I guess the paper, the author chose like a particular function and makes use of, or they chose and they make use of the fact that the certificate complexity of H is very low. And I guess that matters for the overall complexity. Can you comment a little bit on that?
Yeah, so right. I mean, so the way this cheat sheet framework works is, so you take your partial function. You take your partial function and you want to make everything about it easy to prove, because later, so in particular, okay, what do you really want to do? You have a partial function. You want to be able to check whether an input is going to be in the promise or not. But it's possible. But usually, the typical case is that checking whether an input is in the promise is a much harder task than solving the promise problem itself. So it's much easier to solve the function assuming the promise than it is to check whether the input satisfies the promise. So we want to make it easier to check whether the input satisfies the promise. And so one way, the way we start doing that is we start by composing the partial function g with an easy to certify function h, and we're going to want it to be a total function. So we take a partial function g and we put on the inside, we compose g composed with h, where h is a total function that's easy to certify. And sort of the easiest to certify total function is this and/or thing. It's like and composed with or. You know, it's a function on n squared bits, but to certify that the value is 0 or 1 is n bits either way. Like if it's right, to certify that this input is a 0 input, you need n bits, or to certify the input is a 1 input, you need n to show n bits in the certificate, even though the input size is n squared. So it's kind of square root faster to certify than to solve, at least to solve classically. This function also has a nice property that there's a quantum speedup for it that's quadratic, which is the most that we know how to get for total functions without cheat sheets. So without cheat sheets, we only kind of know how to do Grover speedup for total functions. So this function also has a Grover speedup. Anyway, so you compose G with H, and now things are a little bit easier to certify, but they're easier to certify for both classical and quantum algorithms. And so the next trick, the main trick, is basically to then give all the certificates, tell all the certificates in a way that only a quantum algorithm will be able to access. So the idea is we want to give the proof that the input really is in the promise. We want to provide this proof let's say in a separate part of the input, like we would just, so we had our original input to G compose H, I guess. And now we'll add a second part of the input that just tells you what the certificates are. Like, so you can go and check that they're there in the first part of the input. So, but we want the second part of the input to only be readable by a quantum algorithm and not by a classical. So to do that is a bit tricky. So the way it's actually done is that you kind of hide this. So you call this the cheat sheet. So this cheat sheet tells you all the certificates for everything. It kind of tells you everything you might want to know about your function. You want to hide this cheat sheet so that only a quantum algorithm can find it. So you make an array of size n to the 10. You add as a second part of the input, basically, an array of size n to the 10 of potential cheat sheets, but only one of them is right. And then you make 10 log n copies of the original function. So the G compose H function, you copy it 10 log n times. So now there's 10 log n copies of the function G compose H. And those 10 log n copies will index, if you solve them, they'll give you the index of the correct cheat sheet cell. And in that cheat sheet cell, then you will find proofs of, like, certificates for all the copies of H inside of all the other functions. So you basically find proofs of absolutely anything you'd want, that kind of verify that everything satisfies the promise and so on. And so now, basically, to find the cheat sheet cell, you need to solve G compose H. So you need to solve this function, or you need to solve actually log n-ish copies, right? 10 log n copies of it. But solving that, we know, is hard classically and less hard quantumly. Once you do solve it, you can find the cheat sheet cell, which will let you kind of verify that everything satisfied the promise. So I guess the description of the final total function, the final total function is basically going to say, okay, if all the story checks out, if you really get, copies, inputs to G compose H, you get 10 log n of them, and they really all satisfy the promise of G, like all of the promises hold. So if you get such inputs where all the promises hold, and when you check the second part of the input, you check the array, you find a cheat sheet in the right cell, and the cheat sheet correctly proves that all the promises hold. If absolutely everything in the story checks out, then output 1. And if anything in the story does not check out, then output 0. This is the kind of the final function. So this is a total function because we have an output regardless of what the input looks like. And it's a total function that turns out to be easier to solve quantumly than classically, because the quantum algorithm will first assume that all the story is going to check out. So if all the story really is going to check out, then you know how to solve G fast using a quantum algorithm. So then you can sort of solve G compose H using such a quantum algorithm. And then you can solve 10 log n copies. Then you still kind of get your quantum speed up the whole way. You find the right position in the array for the cheat sheet cell, and then you check that all the certificates hold using kind of a Grover-like search on the certificates. So you kind of try to check that everything holds, that proves that all the promises were satisfied. And if all that succeeds, you accept, right? But if it doesn't succeed, you reject. So the quantum algorithm can do all of this. The classical algorithm is stuck not knowing what's going on until it solves these 10 log n copies of G compose H. But G is hard classically. So G compose H is a function that's harder classically than quantumly. So for example, if we assume that G requires n classical queries and 1 quantum query, and then H has a Grover speedup. So H requires n squared classical queries, but n quantum queries. Then solving G compose H for a quantum algorithm will take n queries, but for a classical query, classical algorithm will take n cubed queries. And so you can see why there's kind of a quantum speedup there that's larger than quadratic. And yet the function is going to be total because of this cheat sheet part. Yeah, I don't know. So it's a little bit complicated, but I guess maybe the main takeaway is this possibility of converting. And it's not a quantum only thing. It can work for other measures, but it's in general, it converts partial functions to total functions and retains a little bit of the speed up that you had in the partial function study.
I have a question. So it seems like for this new definition, most of the inputs, when you consider all inputs, would not be valid. Like you'd input 0 if that's what you would output for it not checking out. So is that true? Like that, like in the average case, there wouldn't really be a speed up because you'd almost always output 0.
Yeah. Well, so average case always depends on what is the distribution.
Okay, like for uniform.
So if you're considering uniform distributions, then yes, you won't have a speed up just because the answer is like always going to be 0 pretty much. So for typical inputs, the answer is 0. But the uniform distribution is maybe less of a natural choice than you might think. It's sensitive to kind of how we set things up. So, for example, here's a modification. Instead of let's see. So instead of just this cheat sheet function, take 2 copies of the entire cheat sheet thing. So this entire total function, that complicated definition. Now take 2 copies of it, and we want to compute let's see. I was going to say we want to compute the parity of it or something. I guess for uniform, yeah, maybe that's not the right way to do it. Let's see. I feel like I'm just trying to add more one inputs artificially, if that's what bothers you, basically, that there's not enough one inputs to make the uniform distribution hard. But I feel like just using various simple tricks, you may be able to do that and add more one inputs. So for example, I mean, if you just say, okay, my new function is take 2 copies of the old function and just take their parity or something. Yeah, so I guess you don't add enough one inputs like that. Let's see. Okay, I mean, this is, yeah, I suppose most tricks I can come up with to add more one inputs while retaining, so to make it harder against the uniform distribution or something. I suppose most tricks that I would naturally go to make the function a partial function again. So I guess maybe there is a point here that it's not so easy to do, like retain the function being a total function while making it hard to compute against the uniform distribution. So maybe actually this is a possible interesting question here, whether this is possible to do, to get a function that has a super quadratic speedup, a super Grover speedup, basically, even a cubic speedup for total functions against the uniform distribution. Yeah.
Do you think there might be another, like not uniform, but like less engineered than yeah, not too like overly engineered of a distribution that you'd still be able to get a pretty good average case speed up?
Yeah, so Well, I mean, there's this result called like Yau's minimax that tells you that if you have a worst case lower bound, then there's always some distribution for which you have an average case lower bound. So we kind of know there will be some hard distribution. Obviously it will have equal weight or roughly equal weight on the 1s and 0 inputs. But there will be some distribution on which you will get a speed up here just because this distribution will be hard classically. So of course, yeah, but that's not a natural distribution. So if you kind of want, yeah, so it depends on what you mean by natural distribution. So my normal intuition or instinct is that you can just play with what your distribution is by modifying the function sufficiently using simple tricks. But I feel like most of those tricks actually only work for partial functions. So yeah, maybe since we care about total functions here, maybe that's not true, and maybe it is. Yeah, maybe it is worth asking. Can you get, say, such a quantum speedup in the average case for kind of various natural distributions, for example, the uniform distribution. But if you just ask, can you get an average case separation for any distribution, then the answer is yes, because if you get it in the worst case, like here, then by Yau's minimax principle, there will exist a distribution such that it also holds for the average case against that distribution. It won't be a natural distribution. Did that answer your question?
Yeah, that was helpful. Thank you.
Yeah. Okay. Yeah. Good. So yeah, but I suppose it's worth thinking a little bit about whether we can get, for example, this kind of thing to work against a uniform distribution. I guess my guess will still be that via various tricks. So for example, how would you add more, 0 inputs or 1 inputs? Like you can, I mean, you can kind of add bits to the input, that need to all be 0 on a 0 inputs or but not on a 1 input or something like that. It just feels like, there's a lot of ways for those extra bits to not be all 0, but there's only one way for them to be all 0, and kind of, it feels like by various tricks like that, you could try to change the ratio between the number of 0 inputs and number of 1 inputs. But I don't actually know how to get it to work, so that it remains an interesting question whether we can get this to actually be a separation for the uniform distribution. Yeah. Okay, any other comments on any of the papers, including the one we didn't take up? Okay, so if not, we can end here, I guess. So I will post the readings for this coming week, and I'll also have some notes, and I'll make a short video, I guess. And yeah, and I owe several of you emails on your project, so I will send those as soon as I can. Sorry about that. All right. So if there's nothing else, I guess I will see you next week.